Hi class. Today's lecture is on manifold learning, and as usual, we'll give some motivation and a preview of what's going on. Okay, I need to see what I'm doing. So bear with me. Perfect. Okay. Ideally, what we want to cover in this class and what topics are included in today's lecture is the motivation for manifold learning, and then a little bit about a little bit on multidimensional scaling, MDS, and a section on locally linear embedding, isomap, another maybe not related but interesting approach that is doing the same. All of those methods are striving for the same to solve the same problem that I will cover in the motivations section. And then, despite existence of a plethora of other methods that do the same thing or strive to solve a similar or the same problem, we'll jump into relatively recentish one, but very remarkable, TSNE, T-distributed stochastic neighbor embedding, and talk about something unexpected, I guess, after all of those complicated methods. We'll talk about simple random projections, which actually are related to some of the goals that these methods are trying to achieve. So here we go, motivation. What are we doing? What are we solving? So first of all, data is inherently lower dimensional. And I did say that in the PCA lecture, and I will repeat that again. And the lower dimensionality or the dimensionality of the data is not in our measurement, because we can measure a lot of things from a different angle, but the underlying processes are quite simple. Much fewer moving parts than we actually measure, and those, well, it all depends on scale, but usually we're operating on one scale at a time. Like, we're not simultaneously operating on atomic scale and on the driving a car scale. We are not analyzing individual atom movements, but we're analyzing what those atoms are constructing. So another car that drives past us is made of atoms, but we usually don't need to analyze each of them because at this scale their actions combine. So that's just an aside, but at any given time, at any given, I would say, spatial or operational scale, data is inherently lower dimensional. And what I mean is, so let's take this driving condition. If you look on top and pretend that it's a color image, then it could be a megapixel image with, well, mind my resolution of the animated GIF that I found online. But it could be a megapixel image where each point on the screen, let me, can be plotted with time, right? Intensity with time. So each point, each pixel here can be considered as a dimension, and all possible values of that pixel is sort of the domain, like this values of that pixel where our function could live or our measurement sample could live. And if we took all of them, it's a highly multidimensional space. But really, the intrinsic space is all we care about, that this blob is a car, and this is also a car. Well, maybe we do care about a utility car, or some larger car like a truck separately from the rest. But in any case, a road is a road. We really don't care much about every pixel there on the road at the time of driving, at least if, if we're not paying attention for whatever reason that prompted us to switch to a different scale to the cover of the road. But so my point is, look at the number of colors. You only have very few dimensions, very few components in the underlying picture of the driving conditions. When another situation as well is the way we operate our brains. Our brain gets millions of inputs, sensory inputs, from the neural bundles that come to the brain, sensory areas, temporal for the hearing, occipital for the vision. Then we have olfactory, that is very important, and we're like smelling a lot of things, and have a lot of sensory inputs that enter the picture. Then touch, every little hair on our skin has touch sensitivity, sort of mechanical sensor, and the brain perceives all of that. It's again mega pixel, whatever, millions of dimensions, sensory input. But like, if you touch something, there's only inherently one thing that matters that is happening, and the dimension is very low there. It's not that every sensor is delivering a unique information. So one way to think about is like the sensors are correlated, but it's more complicated than that. Yes, that's the sensors are correlated. That's what I'm trying to say. And but the thing is that there is an underlying dimension. It's like with PCA, where we're finding a hidden dimension by rotating our original coordinate frame. Like, we're measuring two sensors, but in fact what is happening is not in those sensor space, it's in a different rotated space. But what could be happening, and what is likely, what we believe is happening in reality with the brain, or the way we're measuring our data, that the processes that this data unintentionally represents, like, we're just casting a wide net, we're measuring something, but the processes that happening in that multidimensional space are happening within a thin layer, within a dimension in that space, or a surface, or what we call a manifold. I will talk about it in a couple of slides. That is much lower intrinsic dimensionality, and what we assume is locally linear. So how do we, like, what do we do? How do we extract information? So to see how the data is structured, and to see if there are, excuse me, any hidden dimensions in the data, we use exploratory data analysis, and that is the methods I'm describing here fall into that category. So the goal is to find hidden low dimensional structure in the data, and low dimensional representation is used usually for visualization. So remember this invisible gorilla experiment and the famous viral video on YouTube where people are playing ball and you're supposed to count how many passes are made by people in the white, and something interesting happened in in between, but we usually don't notice because we're too busy counting the passes of the ball. And so similar study, a similar experiment was done with data. They I don't have a link for that. I couldn't find it, but so you will have to trust me on that. Students were split in two groups, and one group was given a set, like they both were given the same data set, a column of X and Y coordinates, and one group was asked to just try to find something interesting, and another group was given more specific tasks, like is there correlation between X and Y, and things like that. So the data, actually, if you plot X against Y, you will just see a picture of a gorilla. Uh, that was a reference to this particular video you just saw, to the invisible gorilla. And turns out that people who were not given any particular task, they actually bothered and plotted the data more often and found the gorilla than people who were given the task of finding correlations. So instead of plotting X against Y, they would fit a line and report beta coefficients and things like that. So when you work with any data or any information, and before starting to blindly apply toolbox data from sklearn or from whatever your professor taught you, it's always good to think from the basic principles and to look at your data. So to just see what's going on. Maybe all of your data is mislabeled. Maybe it's full of outliers, nothing in common between the data or anything. But look at your data first, play with your data, make sure that you're not working with garbage, and because garbage in, garbage out. So that's exploratory data analysis allows us, gives us tools to not fall into a pitfall of smart but stupid person, sort of person who knows a lot of methods but actually doesn't understand what they're doing. So the data, we believe, lives on manifold. What is a manifold? And I'm not gonna burden you with formal explanations here. And most of the slides again here are borrowed from Barnabasz Pacasz from Carnegie Mellon. So manifold informally is any object nearly flat on small scales. Well, linear manifolds, well, obviously flat on all scales, and we can approximate circle with a tangent, so basically a smooth surface. So this line is also a manifold. It can be approximated by well, you can always put a tangent and pretend that it's flat at a small scale. Well, for 3D, those are just a few examples of manifolds, but they could be anything as long as they're nearly flat at small scales. That's what I meant. So manifold learning is can we find those flat regions in the data? Imagine this is a manifold, our data, and can we display those flat regions, map them to a two-dimensional space for visualization? Sometimes it's three-dimensional space, but more than three, it's harder for us to visualize and grasp. Okay, so let's look at what I mean in a little more detail. So let's look at this three-dimensional picture of a mammoth, woolly mammoth, or woolly mammoth skeleton rather. And what is happening here, a point I'm pointing to is drawn here in black, and it's also reflected here in the circle. So this 3D woolly mammoth is projected with some algorithm. Don't pay attention which one, it doesn't matter at this point. It's projected or mapped into two-dimensional space. We usually, when we say projection, we kind of imply linear projection, but um, think about this as mapping because not it's not it's not linear and doesn't have to be linear. So there are a few parameters we can vary, like the neighbors that are participating, like in this locally linear uh, uh, decision of what is the neighborhood that is locally linear, and we're flattening it out. And as you see, the points are like the tasks, and the poles got separated. But if you increase the minimum distance, you're getting a different picture. So you can get this mapping where all of the points sort of flat, but less. Or maybe you can get some idea of your data, right? By this process. Even if your data over here on the left is high dimensional, not just three-dimensional, maybe plotting it in 2D can help you figure out uh, that there are some hidden structures in this data. It's another way to plot, and yeah, the corresponding points. Those are just two methods, one against another, and you can change values and see how sensitive the method is. That's the point of this visualization. But in practice, those two methods are striving to achieve the same goals. Um, this is not as interesting because the data is 3D, but look at this fashion and mist data where each point is a fashion item, clothing, whatever bags, I don't know what they would belong to, um, which category, and look how they grouped in the 3D. So even though the input is a 2D set of 2D pictures, we can simultaneously analyze this whole data set. And this is not clustering. We haven't clustered anything. We already knew which are the trousers, which are which, but the algorithms didn't cluster. The algorithm just represents the data in this high dimensional space where each of the images lives in 3D. So you can play with it yourself after the lecture, or like just follow the path here. So there are lots and lots of algorithms for manifold learning. Well, PCA is one of the simplest algorithms. Well, the algorithm is beautiful, of course, but it is learning a linear surface or hyperplane. Then there is multidimensional scaling that we will consider, and salmon mapping that is kind of part of it, or very related. Then maximum variance unfolding, locally linear embedding, a fresh wave of these methods that attracted a lot of interest to the problem. And isomap, Laplacian eigenmaps from the recent to the era. And then the distributed stochastic neighbor embedding that is remarkable in its own right, random projections, and many more. So let's get to the topic, let's see how all of those methods, or frankly just some of them, how they work to unfold data sets that are locally flat but highly intricate. Let's get to the unfolding.